Hello all, welcome back to our channel, and today we are going to discuss a very important topic, that is design of common emitter amplifier. So as you can see on your screen, I have used the schematic editor from the SPICE or any other circuit simulator you can use to draw the basic configuration of this common emitter amplifier using an NPN transistor. So as I see from the direction of the arrow, this is my NPN transistor, and there is a power supply or voltage source with the value given. I have used to source the power to all these circuit elements. So you see the name of the net is V plus, that is connected here, and that is connected here. And another way what I can do, whether there is a connection or not, I will just right click this net. I will right click this and click highlight. So you see that this net is connected here and this net is also connected here. Okay, so today we are going to see the DC analysis of this circuit, and then we are going to see the AC analysis of this circuit, and we are also going to see a transient analysis of this circuit. So when I say a DC analysis, we are talking about understanding the bias point or the Q point of the circuit, or Q point of the circuit. It is also called as operating point of the circuit. Remember, whenever there is a transistor, we have to use it as an amplifier. We first need to bias it with DC voltages, and around that bias point, we have swing of voltages and currents for both input and the output. So this is an NPN transistor, and let me use different color to highlight the collector, base, and the emitter of this transistor. Now, what I do to the base, I have applied this input signal, that is V in 1, and this is a coupling capacitor. This is, let's say, C1. So I am calling it as a coupling capacitor. The role of this coupling capacitor is to block the DC voltage across its two plates and pass the AC that I'm going to apply as a small signal input to the base terminal. Then I have used this resistor R1 and R2 from the voltage source V plus as a voltage division circuit. So just two resistors in series. So the voltage that comes here, which is VR2, helps me to set the voltage at the base of this transistor. So VR2 is basically, you can see, is the voltage at the base. And then I know the base voltage is positive with respect to emitter, so there'll be a small drop of the voltage across this junction, PN junction, which is the base emitter junction of the NPN transistor, and that voltage drop is VBE. Then the voltage at this node VE is basically VR2 minus VBE. That is my voltage. I can also call it as a base voltage VB, but I have named it as a VR2. Why not just named it as a VB? That's much better, because here also you have used different terminal or different name here. So just right click and don't say anything here. Click OK. It's saying you have Let's rather just cut it, and then just click this net and call it VB. Let's say VB, and we'll see that. Okay, so we'll say that small VB, small VE, and this voltage VBE will also be called as small VBE. So let's draw this properly, and let's write it properly also. Okay, so just say call it small VBE. That's much better. So this VE, so VE would be VB minus VBE. Okay, now I have used the RC in the collector, and it is one end is connected to the collector and another end of this resistor is connected to the voltage source. Then I have used this RE. Remember, we have two types of common emitter amplifier. One without RE, in which the gain will be purely set by the resistor RC, and one is with RE as shown on the screen, where the gain will be set by the resistor RC and RE. We know that the gain of the transistor is set by the ratio of these two resistors, RC over RE. Okay, that is the gain of the transistor, RC over RE. Okay, then you have this another coupling capacitor that couples your input signal, output signal at the collector to the load, which is given by this resistor RL. Now there is this capacitor C3 is also is called as bypass capacitor. Bypass capacitor. So what happens? The reactance of the capacitance, which is 1 over 2 pi fc. So if the frequency is 0, that is at when you are processing the signal at DC or very low frequency, then capacitor acts as infinite. So it acts as an open circuit, so as if you don't have it connected there, and your resistor RE is connected from emitter to ground. However, at very high frequency, this XC is tending to be 0 because frequency is very high or infinity ideally. In that case, this capacitor acts as a short, and your resistor RE acts as a short, is connected to the ground by this capacitor. So usually when you design an amplifier, let me just clear the drawing now. When you design an amplifier, there are few parameters that is given, which are called as specification. One is your supply voltage V plus. So in our case, let's say it is 12 volt. Then you are given IC. For example, we are designing it for 10 milliampere. Then you are given load. So let's say it is also 10 kilo ohm. Okay, and then transistor is also given, and some other parameters can also be given. So now we will see how to obtain the design equations, and step by step we will then choose the components values, and accordingly we will see the operating points, all the DC voltages and the currents in the circuit. Will make sure the transistor is biased in an active region. That means the base emitter junction is forward biased and the base collector junction is reverse biased. Okay, so those here is your base, here is your emitter and your collector, and this is N, P, N. Okay, so here will be the circuit connections. So the first equation that I am going to explain to you will be like this. Just hold on. The first equation, we will say that here is your collector, here is your emitter. So the voltage drop across this collector and emitter will be VCE, and that equation can be written as VCE. This voltage will be VCC or V plus minus IC times RC. Okay, so this is the equation. You can see that. So you can say that ICRC would be equal to VCE or V plus minus VCE. Now, RC therefore can be chosen to be V plus minus VCE divided by IC. So value of V is known to you. For example, we are choosing 12 volt. So 12 volt is there minus VCE is generally chosen as VCC by 2. So we can say that we can write here VCE is chosen as V plus by 2. So if V plus is 12 volt, then it will be like 6 volt divided by the value of IC is given 10 milliampere. Okay, and that's your value of RC. So we'll see that it is 6 divided by 10 milliampere, and that comes out to be 0.4 kilo ohm. Just let us calculate that. So it is 600 ohm. Okay, so let's do that. We'll do one thing. We will just select the value of the resistor to be 600 ohm. So let us write here 600 ohm and click OK. That's it. Now we selected that value, and the second task is to similarly we choose the values for all the components. Okay, so we'll do that in a moment. So next task is to decide the value of resistor RE. So generally RE is chosen to be about 10% of RC. So RC is 600 ohm. So the value of your resistance RE will be 60 ohm, right? So we'll choose that. So let me do that. So here we'll right click and we'll put the value 60 ohm. Okay. Now next task is to decide the values of other. We know the value of IC, that is our 10 milliampere, and the beta of this transistor can be known. So let's find out the transistor we have chosen. What is the beta of this transistor? Right click it and click pick new transistor, and the first transistor, as you can see, we have chosen where the beta of this transistor is about 200. Let me highlight it here. So beta factor is 200. So why not just take that into account to get the value of IB? So what we'll do, we know that the beta is about 200 and IB is beta times IC. Sorry, the IC is beta times IB. Therefore, IB will be IC over beta, which is 10 milliampere divided by 200. And let me calculate the value of it. So tell me what is the value of IB. 10 milliampere divided by 200 equals how much? It comes out to be 50 microampere. So you see, we got the value of IB as well. Now, next task is to determine the value of VE. So we first know that VE, to calculate VE, we need to know IE. And IE is IB plus IC, which is equal to 50 microamp plus IC is your 10 milliamp. So it should be, how much it should be? Tell me that. So we can say that it's approximately equal to 10 milliampere only, because the base current is very, very small as compared to collector current, and therefore IE and IC are can be approximately equal, and VE therefore is IE times value of RE. But RE is 60 ohm, we know that, and this is therefore 10 milliampere multiplied by 60. So that comes out to be 600 millivolt. So that's great, 600 millivolt. Okay, so we are solving it one by one. So next job is to determine the value of VB, and VB can be calculated as VBE. This is the VBE plus VE, right? Because VE, we said that it will be VB minus VBE. So VB will be VE plus VBE. So it will be written as VBE plus VE. Now for a silicon transistor, VBE is generally 0.7 volt plus VE we just calculated, it is 600 or 0.6 volt, 0.6 volt. So it is coming to be approximately 1.3 volt. So that's how it is working with the way it is shown. Now next step is to calculate the values of R1 and R2. So we need to apply a Thevenin's equivalent network. So remember, Thevenin equivalent says that any network can be represented by a Thevenin's voltage and an equivalent resistance in series with that, that is Thevenin's resistance RTH. Okay, and this is an open circuit that you measure it across. So Thevenin's voltage from this network can be written as VTH would be the R2 divided by R1 plus R2 multiplied by V plus, which is 12 volt right here. And RTH can be given as the parallel combination of R1, R2 divided by R1 plus R2. This is a parallel combination of R1 and R2. Now, there is a resistance that you need to calculate, which is R in. That is the resistance, input resistance, that is looking into the base of the transistor. This is the base, remember, and you are looking into the base. So you need to calculate that resistance. Okay, and R in can be calculated like this: R B plus RIB divided by, okay, just a second, let me check that out. Right, so your R in can be written as, let me write here, RTH into RIB divided by RIB plus RTH, where RTH is this resistor and RIB, this is an input resistance, okay? Input resistance, and RIB is the resistance looking into the base, not Rin. Okay, Rin is the input resistance of the circuit and RIB is the resistance looking into the base. And the value of RIB can be given as 1 plus beta times RE. Okay. So we can get the value of RIB because we know the value of RE and beta. So beta is 200 times 60. So 200 times 60 would be like 60, 120. So it's about 12K. So RIB comes out to be 12K. And once you know the value of RIB, you got to know the value of RTH. So choose a value of, let's say, one of the resistor, and then you can get the value of RTH. Let me just check that out, how you can do that. So we forgot to add one more parameter. R in is also given. So let's say it is 200 kilo ohm. Okay, so you know R in is 200 kilo ohm, and RIB we just calculate 12 KO. So plug in these two values in this equation to get the value of RTH, which is the parallel combination of R1, R2 and R1 plus R2. Okay, so how to calculate that? So it would be like RIB will be your 12K plus RTH, and this will be equal to RTH times 12K divided by R in, which is 200K. Okay, so you got to understand that. So it would be, if you solve this, you need to get the value of RTH. You will get the value of RTH, and then with the value of RTH, you have to write one more equation, which is VBB is also given as VBB with VTH. Actually, VTH is also given as IB times RB, IB times RB, not RB, RTH, RTH plus VB, and your VB is the voltage that we calculate initially. Where is the VB? VB. Did we calculate that somewhere? Let me check. Yeah, where is the VB? Let me check that. Here, we calculated VB to be 1.3 volt. This is small VB, right? So from these equations, you get the values of R1 and R2. You just solve that. So just choose one of the values of the resistor and you will get you can calculate the value of other resistor. So I am choosing the values of the resistor to be, let's say, 1K each. This is like 10K, for example. I want to choose 10K here. And the other register also I want to choose 10K. In fact, it has to be chosen by the calculations that the formulas that we calculated. So 10K each. So these two values will maintain the base current with the value what we calculated. Now the final is to understand how to calculate the values of the bypass capacitor C3 and coupling capacitor C1 and C2. So there is simple formula to get the value of C3. We just know that the capacitive reactance is Xe, which is 1 over 2 pi Fc. And we are going to say that if you want to know the value of bypass capacitor, so it has to obey the equation, so that reactance of this bypass capacitor should be less than or equal to value of Re divided by 10. So you from that you can, so value of Re is 60 divided by 10 will be 6. So it should be Xe is 6. So for a given frequency, you can get the value of that capacitor. So for example, your frequency is 1 kilohertz, uh, or let's say 10 kilohertz. So let's say your C would be 1 over 2 pi into your frequency of operation is, let's say, 1 kilohertz. That's much better. 1K into 6. That is how you have to calculate. So let's calculate that and plug in that value right here. It comes out to be 26 microfarad. Let me just write that. 26 microfarad, or just mu. That's it. Similarly, choose C1 and C2. We'll apply the same formula. XC is equal to 1 over 2 pi RC. So your CC1 is should be less than or equal to Rin divided by 10. Let me write here your CC1, which is here, the value of it. CC1 should be less than or equal to Rin divided by 10. So Rin is 200 kilo ohm right here, divided by 10 is like 20K. But it should be XC actually, not the CC1. All right, so we'll have that formula. XC1 should be about 20,000. And then therefore CC1 would be, this is XC1. So the CC1 should be 1 over 2 pi 1K multiplied by 20K. Does it make sense? We'll check that out. So we'll plug in the value. It should be, looks like very low. So this capacitor value comes out to be 7.96 nanofarad. Let's do that. 7.96 nano. And now finally, this capacitor, which is C2, that finds the equation of XC is less than or equal to RL divided by 10. So RL is our 10 kilo ohm, and divided by 10 is like 1000. So the value of C2 would be 1 over 2 pi F times 10 kilo divided by 10. So 1000 or 1K. So it is 1000. So we'll calculate the value of C2. Let's see how much C2 comes. That comes out to be 0.15 microfarad. So 0.15 microfarad. So that's it. Let's put the value of RL here. RL is your 10 kilo ohm. So we have actually put up all the values of the components, including capacitors and resistors. So in the next video, we will simulate the different analysis and see how our theory calculations match up with the calculated values. So till then, stay tuned until the next part comes in. Wish you happy learning.